Hi, my name is Zhao Wei. I'm a PhD student at the University of California, Santa Cruz. This paper I will be presenting today is titled Federated Bandit, a Gossiping Approach. In this work, we propose a novel, fully decentralized bandit learning framework that handles heterogeneous data sources with a privacy guarantee. I'd like to thank my colleagues from UC Santa Cruz and the Stony Brook University. Let's say a motivating example. Consider a scenario where there are multiple hospitals. They want to test the performance of different treatment plans, but the data sets in different hospitals may be non-IID. In other words, each hospital may only have a biased data set. For example, when hospitals test the treatment effectiveness of Arm 1, based on the local observation of Hospital 1, there are 4 positive feedbacks and 3 negative feedbacks. Then the reward can be estimated to 4/7. This estimate may not be true due to the biased data distribution. To reduce the bias, we may need to refer to other agents. In this example, based on the local observations, Hospital 2 estimates the reward to be 2/7, since there are 2 positive cases and 5 negative cases. Combining the estimates from both hospitals, we can get the true global reward, which is 3/7. This example shows when the local data distribution is biased or heterogeneous. If there is no collaboration or federation to reduce the bias, even though we have sufficiently many examples, we will still converge to a biased reward, then make a biased decision. The main focus of this paper is to handle the data heterogeneity in Bandit. In the MAB settings, we consider several challenges. The first one is data heterogeneity. As shown in our motivating example, the heterogeneity indicates that the data sources of different agents are biased or noisy. The problem cannot be solved if we only focus on one data source. Intuitively, the collaboration or federation among agents helps to reduce the effect of data heterogeneity. When different agents share their knowledge, it is generally hard and expensive to call for centralized efforts to coordinate the global data transportation. The global operation may even be forbidden due to some privacy regulations. To avoid the use of a central controller, we try to propose a fully decentralized solution where agents only need to share their local knowledge with several others. Besides, during federation, we need some techniques, for example, add some noise to data sources to guarantee the agent's privacy in the worst cases. We propose 2 algorithms to handle these 3 challenges. Firstly, as the first milestone, we focus on the data heterogeneity in a decentralized bandit setting and propose gossip UCB. This can be seen as a simple case where the data privacy is not specially protected. Next, build on gossip UCB, we implement the popular differential privacy method to ensure the worst-case privacy, even with a powerful adversary. For each algorithm, we prove the upper bound for the regret. In online learning problems, the regret is accumulated difference between the optimal reward and the actual reward. Intuitively, the regret should be a function of total time, the communication graph among agents, and the privacy level. Specifically, we use the lambda 2 to denote the connectivity among agents, which is defined as the second largest eigenvalue of the gossip matrix. Generally, as shown in these 4 examples, a smaller lambda indicate a better graph connectivity. When the graph is not connected, lambda equals to 1. We summarize the orders of regret bound in this slide, where n is the number of agents, m is the number of arms, t is the total time. We can see the regret is proportional to a polynomial of log t and inversely proportional to the graph connectivity and privacy level. Our algorithm can be summarized into 3 steps. At step 1, each agent needs to check the local consistency with a nearby agent. This step is to keep all the agents on the same page. With the result of local consistency check, we can make locally consistent decisions at step 2. For example, if the local consistency check is passed, agent I will make Bandit decisions and select one arm from M arms according to the belief of each arm. Otherwise, they need to pull one particular arm to push consistency. Once the action is taken, the agent will receive a private feedback from the target arm. The feedback is protected based on differential privacy. After all agents getting their feedbacks, we'll go to step 3, where one communication link will be activated and 2 agents on this link will exchange their private data. We call this step gossiping. Then we will go back to step 1 and run these 3 steps repeatedly. Let's see more details. Firstly, let's discuss the first milestone, gossip UCB, where we focus on the data heterogeneity and the decentralization. In gossip UCB, when agent I pulls one arm at time t, it will get a local feedback. This feedback can be observed locally. If from the global perspective, there is an ideal feedback or global feedback, the true regret is defined on this ideal global feedback. The local feedback may or may not be the same as the global one. Likewise, the expectations of both feedbacks may be different. In the traditional homogeneous setting, many works may assume local feedbacks have the same expectation as the global one. Thus, federation can be used to speed up the convergence. However, in the heterogeneous setting, when local mean is different from the global mean, the problem cannot be solved without federation. In this paper, we assume the global average of local mean equals to the global mean. We use tilde x to denote the estimate of local mean, which is the sample mean of local observations. The other estimate we need to maintain is theta, which is the estimate of the global mean. The action is taken based on the estimate theta and a specially designed upper confidence bound. Due to data heterogeneity, the local mean not equals to the global mean. Thus, the sample mean is biased and shouldn't be identical to the estimate of rewards. Then the remaining problem is how we update theta to make it unbiased to the global mean. We use the idea of gossiping. At each time t, one edge is activated. Only the agents on the selected link exchange information. For example, agents on both sides of the green active link are selected to exchange their estimates. For the agent on the top, the estimate before gossiping is 4. During gossiping, a new estimate, 6, is received from the other agent. Then by taking an average between 4 and 6, the estimate is updated to 5. Similarly, the agent on the bottom receives the estimate 4 and updates the result to 5. Other agents do not update. This is the classical gossiping. Classical gossiping only captures the static information. In bandit problems, in addition to exchanging information with others, we need to evolve the new information from interacting with arms. Specifically, we use a gradient-like mechanism where each agent will calculate a different delta based on the current local observations and the previous local observations. Compare with the classical gossiping, which is shown in red. The activated agent on the top needs to add gradient delta 1 to the gossip information. The agent on the bottom will calculate delta 2 based on its own local observations. Besides, different from classical gossiping, where inactive agents do not update, we need all the other agents perform gradient update in Bandit gossiping, where the new estimate equals to the old estimate plus gradient delta. We show more details of gossiping in this slide, where red color indicates the gossiped information and the blue color indicates the gradient based on the local sample mean. The pseudocode shows the detailed equation that we use for gossiping update and normal update. There is a consistency issue in Bandit gossiping. Gossiping enables agents to share their information, but it is hard to ensure each agent is close enough to the true estimates. Note that the true estimates of arms depend on the global estimates, which is an average of all the local estimates. Thus, intuitively, the local calculation of confidence bound also relies on other agents' number of pools. Consider an example where, according to agent 1's knowledge, arm 1 is selected 100 times by agent 1, but only twice by agent 2. However, based on agent 2's knowledge, arm 1 is actually selected 100 times by agent 2, but only twice by agent 1. This happens when agent 1 and agent 2 are far away from each other and the knowledge toward others cannot be updated in time. When estimating the confidence bound, if according to agent 1's record that agent 2 only selects twice, agent 1 may believe arm 1 is still underselected and decide to select more. Agent 2 may also decide to select more due to the same reason. But the fact is, both agent 1 and agent 2 have already selected arm 1 100 times, which is enough. To avoid this case, we require each agent to share the number of local pools with nearby agents, which is a decentralized synchronization in selecting the same arm. With our local sharing strategy, we can first prove the local consistency, which indicates that the number of local pools is close to the local estimate of the number of global pools. This result makes sure the local estimate is not a bottleneck. Furthermore, we prove that the maximal number of local pools will not be greater than twice of the number of local pools of any agent. This result helps us bound the information inconsistency due to the propagation delay and facilitate a fully decentralized solution. By analyzing the coupling effects of gossiping and bandit learning, we prove the concentration bound for local estimates in theorem 1. In this bound, with some conditions and a high probability, our local estimate of rewards is close enough to the corresponding global mean. The concentration is determined by the number of local pools. It is worth noting that the term C should be related to NIK from all agents. Thanks to the global consistency, we can get rid of accessing the global information and only use the local NIK. Let's briefly overview the proof of the regret upper bound. Firstly, we provide guarantees on the consistency among agents, where we analyze the information propagation and the actual local consistency, then prove the global consistency. The global consistency further helps us to design an upper confidence bound that only relies on the local information. Thus, the gap between the local estimate and its expectation can be bounded locally with a high probability. The gap between local expectation and the real global mean can also be bounded by some gossiping results. With all of these lemmas following standard Bandit proofs, we can give the regret upper bound for gossip UCB. Then we introduce implementing differential privacy in Fed UCB. Differential privacy provides the worst-case privacy guarantee for our algorithm. It is necessary because directly leaking some information that might appear to be anonymized can be used to cross-reference with other datasets to breach privacy. The idea behind differential privacy is that if the effect of making an arbitrary single substitution in the database is small enough, the query result cannot be used to infer much about any single individual, and therefore provide privacy. Different from many cases that protect the privacy of static data, we need to make the whole sequential problem private. In other words, the local observations at each time t need to be private. If we naively add Laplacian noise to each observation, the noise level needs to be t over epsilon. Then the summation over all the t noise terms at time t still keeps epsilon differential privacy. However, the noise in this method is too large and will severely hurt the convergence. In FedUCB, we adopt the idea of partial sum and add Laplacian noise with a parameter of log t over epsilon, following a tree structure. For example, when we get the observation at time slot 4 or node 4, rather than adding all the noisy observations from node 1 to node 4, we can only add one noise term to a pseudo node 1, 4. Similarly, for time slot 6, we only need two noise terms with index 1, 4 and 5, 6. For time slot 7, we only need three noise terms as shown in this example. Then, at time t, we will sum about log t IID Laplacian noise terms, and the noisy level of each term is log t over epsilon. Thus, we can still guarantee epsilon differential privacy. With this method, per sample-wise, the noise is much lower than before, thus the convergence would be much faster. We also analyze how differential privacy affects the concentration bound. Compared with that of gossip UCB, there are mainly two changes. One is at the upper confidence bound, as shown in the blue circle. The other is at the probability, as shown in the red circle. We have some experiments on synthesized datasets and UCI datasets. More details can be found in our paper. This is the main content of our paper. Thanks for your attention.